All right, in this example, the problem says, suppose that an alligator population number initially, so the population initially has 100 alligators. Okay, so the time of 0, there are 100 alligators, and that its death rate, the delta here, delta of t is equal to 0, which means that no one is dying. So here, no one is dying, at least in terms of the time frame that we're interested in. We're assuming that delta of t is equal to 0 for this problem. It further says, if the population birth rate, so beta of t, the birth rate is equal to 0.0005 p. In other words, it's a small scale factor to the original population. So whatever the population is initially, or at some later time, this small scale factor is the proportion to which the population's birth rate is changing. And so we can utilize this information then to plug into our differential equation and create a population projection over time based on this information. Okay? All right, so let's go ahead and do that. I'm going to first recognize that this quantity right here is the same thing as 1 over 2,000, which will help us to in general, instead of writing a bunch of decimals, the writing as a fraction will be a little bit easier to keep track of everything. Okay? All right, so let's go ahead and plug this into the differential equation. So we have dp dt is equal to, our beta of t is here, which is going to be p over 2,000. And then I'm going to subtract their death rate function is 0. It's a constant function of 0 there. And we're going to have a times a p here. Distributing that in, okay, this is going to give us a really nice separable differential equation. So we have dp dt is equal to p squared over 2,000. Okay, so I'm going to invert and multiply both sides by this and move the dt over here, and that's going to yield a dp times 2,000 all over p squared is equal to dt. Okay, and now I can simply just integrate both sides here. So factoring out the 2,000, this is p to the negative 2, the constant factoring out because it doesn't affect the integration. dp is equal to the integral of dt. So integrating on this side, I'm going to get t, and I'm going to put the constant here, plus c. Here I'm going to get a negative 2,000 p to the negative 1. And then solving for p, this is like 1 over p, so I'm going to flip these over and move, which is the equivalent of multiplying both sides by p and dividing by this. So you end up with 2,000 over t plus c is equal to p. So this is our population formula for in a general case. It's a family of curves, and so we need to solve for this initial condition, which is given in the starting population of p of 0. So if I do that first, I'm given that p of 0 is equal to 100. This is negative 2,000 over t, which is 0 for our pop, plus c. And so what number would this have to be in order to be, this is just 2,000 over c, which, what does that make that to be 100? Well, if you cancel out, you can think of it as canceling out, and you're left with negative 20 over c is equal to 1. So that means that c has to be equal to negative 20. So c is equal to negative 20. Okay, and so finally we can rewrite our full formula for the population. Our model is negative 2,000 over t minus 20. Okay, so there's our function of t, and now the question was asking us to determine how long does it take for the population to double. So what we're trying to figure out is what time does, if I plug in this time, I call it a time of 2, in other words population, for the population to double its initial population. Okay, so 2 times p0. Our p0 happens to be 100, so we're going to have 200 in our population, but notationally speaking, this is what we're doing. Okay, so I'm going to plug in this t into this equation and set it equal to 200. So this is going to give me 202 times 100 for the initial population is equal to negative 20, or 2,000, sorry, times t. This is the t that we're looking at that makes this happen. And so just like before, I can cancel out, make that a 1. And then if I move this over here, this is going to be 1 now. So this is t minus 20 is equal to, it looks like, a negative 10. Yeah, negative 10. And then if I add 20 to both sides, I get t2 is equal to negative 10 plus 20, which is equal to 10. And the problem said that was that days? Oh, I didn't say actually. So whatever units of time. So if this is days or weeks or who knows how long this is in terms of units of time, but the time for the population to double is 10 units of whatever time that is. And then the last part says what happens in the near future for these alligators. Okay, so what happens in the near future. Okay, what happens in the near future? And so one way to kind of think about that is if you plot this specific p of t as negative 2,000 over t minus 20, what does this graph look like? And so this graph has a very sharp ascent with a value there, and so p of 10, we're at, it's not quite, should be a little bit like there. Okay, so that's twice. If this is 100, this is 200, but then quite after that, it explodes quite quickly, and so eventually this population is going to quickly reach some sort of carrying capacity of the land. It can't go, realistically speaking, the population will reach some sort of maximum carrying capacity, and then either competition through resources or death or fight or whatever the case may be, this population eventually will reach some sort of carrying capacity and it'll level off and die. And it'll reach some stability point later on, but immediately after, what's going to happen is that for some time after, sometime after this initial starting point, this is t equals 0 here, the population is going to grow essentially exponentially. It's growing very quickly until the carrying capacity of the land is reached. Okay, all right, hope that was helpful, and I will see you in the next video.